All right, so now on to our next concept. So I'm going to introduce pipeline logic, and I'll introduce that with this example. So in this example, we're implementing a computation of Pythagoras' theorem in hardware. So we're computing the distance c as the square root of a squared plus b squared. And to do that, we need a circuit that's going to square a, square b, then add them together, and then take the square root. And in a modern processor, we're going to be running at, maybe a gigahertz, and we can perform so much logic. Maybe it's reasonable to do 20 stages of, or 20 gates deep of logic within the clock cycle. But after that, your logic would be taking too long to catch the next clock edge and be captured in the next set of flip-flops. So this logic is fairly deep, too deep to fit in a single cycle. So we're going to distribute this computation over multiple cycles. So in the first cycle, we're going to do our squaring, square a and b. Then we're going to capture that in flip-flops. And then we're going to add those values together, and again, capture the result in flip-flop, and then take the square root. Now, square root itself would take multiple cycles in reality. This is just an example, so let's keep it simple here and assume that we can do the square root in a single cycle. So we just looked at sort of the RTL mentality version of this circuit, where we're explicitly defining our computation and our flip-flops. Transaction level Verilog gives you the ability to model this in what's referred to as a timing abstract representation. And there are different forms of timing abstraction. I'm going to talk about the form of timing abstraction provided in TL Verilog. So with TL Verilog, we give ourselves a pipeline, and we'll call it calc. And that pipeline has multiple pipeline stages, and we're going to provide this computation within those stages. So mainly the difference between the top and the bottom is I've drawn a pipeline and I've drawn lines for the pipeline stages. I haven't drawn the flip-flops. Right? The flip-flops are implied by the fact that I have a computation in one stage feeding into a computation in the other stage, in the subsequent stage. So to get the value from one stage to the next, I need a flip-flop. I don't need to bother drawing it. It's crossing a cycle boundary or stage boundary. All right, so it's basically that simple. So looking at the code for this, so you'll see a very direct correlation here between the picture and the code. We give ourselves in the code a calc pipeline. It has stages 1, 2, 3, and within those stages we have logic expressions. So very straightforward. And this workshop is not about language. We're going to use TL Verilog as the language to work on the circuits that we're working on. We're not going to talk about Verilog or System Verilog, but since I'm on this one, pipelines in particular are something that is a little bit awkward to code in traditional RTL languages. And just as a point of comparison, you can see here the TL Verilog versus the Verilog has a very nice code reduction and is a lot easier to just visually understand. There are different ways to code things in Verilog. This is one industry best practice. All right, so the code reduction is a very nice property of TL Verilog modeling. Reducing code reduces bugs, simplifies everything, speeds up the design process. That's all good. The main point, though, of timing abstraction provided through these pipelines is to separate the function that's being performed from how you're implementing that function. So in this case, how you're implementing it, meaning exactly what pipeline stage are you performing the calculation. It doesn't matter. You're performing the same calculation either way. The difference is timing, and the overall behavior of your circuit isn't affected by that timing. And we'll see more interesting examples later on of how pipelines interact, and but through all of this, you'll see that the timing abstract modeling that's provided by TL Verilog is giving you this property that you can change the stage bucketing with a guarantee that you're not changing the overall behavior of your circuit. So in this example that we're looking at, we're starting out with our original pipeline, and the pipelines are conceptually infinite in both directions. But we've got our logic spread across 3 stages, and if we now need to spread that logic over more stages, we can do that. Why would you want to do that? Well, if we're taking this design that we started with and then implementing it in a different context where maybe our AA signal is available on one corner of the die and we need to produce CC on another corner of the die, it takes time to get signals to propagate from one corner of the silicon to another corner. Could take as much as 25 cycles, even in upper level metals on today's silicon. But here we're just stretching this out with an additional 2 cycles, so we give ourselves 2 cycles of transit. And to make that implementation change, we only need to change the stage bucketing of our logic. The logic expressions are still the same in the same pipeline. And because our change is limited just to the pipeline staging, we have a guarantee, 100%, that we're not impacting the behavior of our circuit. The one thing that you can do is you can break the timing of your circuit, meaning by changing the timing, you're trying to consume something that hasn't yet been produced. And we can view that as an implementation issue, not a behavior issue. Okay, so again, not focusing here on Verilog or System Verilog, but point being, making a change like this, and I can't tell you how many times, how much of my life I've wasted making retiming changes in RTL like this. But it's fairly significant surgery with plenty of opportunities for bugs.